Hi, good evening, everyone. I, Dr. Jyoti Gautam, welcome all of you on behalf of the Digital Water India subgroup under the Digital Water Program of the International Water Association. I work as an associate professor in the CSC department at Sharda University, India, and it gives me immense pleasure to be part of this webinar, which is organized by the Digital Water India subgroup under the umbrella of the Digital Water Program of the IWA. The title of the webinar is Artificial Intelligence in Urban Water Systems. Now, I would like to take a brief introduction about the experts. So we have the experts, Dr. Bruno Branton. He is an associate professor at the Federal University of Minas Gerais, UFMG, Brazil, where his research focuses on artificial intelligence, water distribution systems, hydraulic modeling, and data-driven solutions for water resources management. He leads and collaborates on interdisciplinary projects involving machine learning, explainable AI, digital twins, and operational optimization of water infrastructure. He also serves as an associate editor of the Journal of Hydroinformatics, contributing to the advancement of research at the intersection of hydroinformatics, data science, and water engineering. Now we have another expert, Dr. Manuel Herrera. He is a lecturer in hydrology at Newcastle University and a committee member of the Strategic Asset Management Specialist Group at the IWA. He is also an associate editor of IWA, Water Infrastructure, Ecosystems, and Society. His research focuses on digital water, urban water systems, and the use of physics-informed and structure-aware machine learning to improve forecasting, reliability assessment, and resilience in water infrastructure networks. Through his recent fellowship with DAFNI, the UK's Data and Analytics Facility for National Infrastructure, he is advancing work on trustworthy AI and data-driven decision-making for the adaptive management of urban systems. Now, Bruno, it's over to you.
Hi, hello. So thank you for the opportunity to talk about a bit about artificial intelligence on our water system. Mainly, I will talk about the use of artificial intelligence in water distribution systems. That is my main field of research and also work. So that's not new that we are using artificial intelligence in our systems. More than 20 years ago, something about machine learning started to be used on water distribution. But today, I would like to go on the direction of what we are doing and the opportunities that we have nowadays in our hands concerning the idea of artificial intelligence for urban systems, more specifically water distribution systems. So for the next slide, please, we can see one of the biggest problem that we have on thinking on water distribution systems nowadays are related to the climate change and the reduction of water availability around the world. So many parts of the world are starting to be stressed by the absence of the water, meaning that we need to manage the water systems that we have better. Thinking that we are talking about 2 billion of people without water, without potable water to drink, without a good water distribution system, and even the countries like Brazil that is known about the water availability, we have now year by year seeing the stress in many cities. So the point is, when we think about a better management of water distribution system, we can think about the opportunities that is coming with the availability of data, because nowadays we are increasing a lot the monitoring of water systems, and with the data, what we can do using artificial intelligence. So next, we can see this cycle about challenges and opportunities. If in one hand we have many challenges concerning the water management in urban zones, not only I comment about the stress of the droughts, but we also can think on the stress when we have floods and then we don't have enough water to be delivered. The point is the intermittence of systems, for example. And then, in a parallel way, we are seeing many times problems with energy. So the availability of energy or the cost of energy, electrical energy, are so high. So if we do a mix of droughts or floods that are leading us to intermittent systems because we are not able to deliver water, combined to high cost of energy, we arrive on this big challenge that is how can we manage our systems. So in this line, what we are seeing nowadays are an increasement, but really important increase on the monitoring of the systems. So we can use remote sensing or many other kind of things to monitor the water source or even the quality of that source, or our systems like measuring pressure, measuring flow rates, measuring the quality of the water that we deliver to people. So we are increasing a lot the amount of data that we have. With this a lot of amount of data, what we can do, this is a good question, because we can be like 20 years ago, just storing that data and observing what is happening, or we can go for predictive models. Predictive models are much more important when we think about this kind of um, this kind of better practices, let's say, because predictive models can uh, help us to understand a bit the future, the trends of future, and then help us to understand if what we estimated for future is happening, because we are modeling, we are mentoring constantly the system. We could check both things. For example, if I have a contamination, but I have a predictive model of water quality, probably my predictive model of water quality will diverge of what I'm measuring, and this is an indication that I have an anomaly in my system. So this kind of predictive model can help us to have a better idea that what's happening in the system, but also we can merge this with smart metering. It's quite common nowadays that water utilities start to do smart meters, place smart meters in for the users, meaning that in real time or almost real time, the measurements of water consumption is delivered to the water utility, and the water utility can use this information, for example, to have a better control of the demand. For example, this is super important when we think about intermittencies, but also for leak detection, for example, or because if a user has a leakage inside of the house or an apartment or in a building, the real-time monitoring, the real-time of measurements of smart meters can help us to detect these leaks as soon as possible, reducing the waste of water and improving the management of the systems. And also with this kind of real-time measurements and real-time estimation predictive models, we can think about real-time operation. So when we do an operation, for example, changing a pump point or changing a valve point operation, we change the topology of the system somehow, trying to improve the efficiency, energy efficiency, hydraulic efficiency of the system. And this will give us a hydraulic answer, a hydraulic response that can be measured again by our system monitoring system, that will feed again our predictive model, that will be again compared with the smart metering and support the real-time operation. So this cycle that I'm showing here is trying to translate the many opportunities that we have using artificial intelligence, because using artificial intelligence we can, for example, fulfill data that is coming from remote sensing or from monitoring points that have problems, or we can use those data to support the predictive models. So we can use artificial intelligence for predictive models. We can use artificial intelligence to better compare, to better model the data that comes from smart metering. And maybe one of the most interesting point that I will talk today is about how can we at real time estimate the hydraulic state of the system and use this for leak detection, so the real-time assessment of the system. So let's go to the next one. We know that water distribution systems are built by pipes, valves, pumps, and the connections to the users. So this gives us a really important dynamic, because when users are pushing water, so they have the demand of the system, the dynamic of the water, the hydraulics in pipes are more in stress, let's say, because they are moving, the water are going there. But when you go to the night, when people are not consuming more water, so the pressure go high because people are not consuming. So this dynamic is quite important for thinking on the operation of the system. And usually what we do until today, is still using the hydraulic laws for doing computational models of those systems. This is super interesting and super important for sure, but we have a lot of uncertainties. And linked to this uncertainties and that high dynamic of system, we have the failures. So basically, we can have pipe breaks or small leaks, or stopping completely the service. We can have contaminations. So we are talking about a super complex system that usually are underground, so we cannot see what is happening there. Combined to high and important stress, hydraulic stress, thinking on water availability. So can we go to the next again? When we do a classical hydraulic model, we should know, or we should calibrate the water demands, the pipe roughness, the main feature of the pipes, the operational rules, and all those anomalies that mainly we don't have control about it. So even if I have data from monitoring system like pressure and flow rate, and I have a topology of the system, I have the information of the project, how is built that water distribution system, I should calibrate water demand, pipe roughness, or other features of pipes, the operational rules. And even if I know everything about it, I still have events that I cannot control, like leaks or other kind of things. So nowadays, I'm maybe not so new about it, but it's in a high point, the use of artificial intelligence for surrogating the classical computational models by using artificial intelligence or machine learning. So basically, what we do during a calibration of computational model. So basically, we enter with pressure and flow rate that we are measuring the field. We calibrate those parameters. I can select some of them. So I try to change those parameters to find a match between what I'm measuring in the field and what I have in my computational model. One way to do a surrogated model or a meta model is basically still enter with, we can go to the next slide. I guess it's better to see this. So basically we have our water system here with some monitoring points that, as I comment to you, pressure or flow rate or even other kind of things, kind of hydraulic states in some points. So basically I enter with this in my artificial neural network or in my machine learning model, any one that we could use to model this. And this will do the role of the computational model. Basically, for example, if I have an APA net model, that is a classical computational model for water distribution systems, this artificial neural network will do the role of my APA net, but not using the variables that are uncertain for us. Like we are not entering with demands, we're not entering with roughness of the pipes, we are entering with what we are measuring in the field at real time. So basically I have encapsulated on those pressure and flow rate measurements. I have encapsulated there all those uncertainties that I cannot have a lot of idea what is the rule of each one, like demand, anomalies, roughness. So basically measuring in the system pressure and flow, I encapsulate everything there. I enter in the neural network with those information, so basically pressure and flow rate mentioned in the field, and my system, my neural network, will give me pressure and flow rate in the complete network, basically surrogating the EPA net model without the need of calibration of those parameters. This is super interesting. This is not exactly new. Um, and it's very interesting because we are talking about encapsulating uncertainties on the measurements. We are talking about fast simulations because we don't need to run EPA net several times when we think, for example, in an optimal operation or an optimization that we should run EPA net several times. So we are talking about more computational efficiency too. But it was a problem until a few years ago because when you do this estimation of pressure and flow rate, for sure, if we are right, if the estimation that we are doing are right, we should be able to comply with the physical laws, the hydraulic laws, by basically talking about mass conservation nodes and energy conservation in the pipes. The point is, of course, a neural network is an estimator, is as a predictive model. So I can have errors in this estimation, and those errors uh, can lead us to a not exactly physical based answer or a physical consistent estimation. What I'm talking is, imagine that in this pipe is arriving in a pipe P1 here is arriving 10 liters per second, and in the pipe P1 2 here is arriving 5 liters per second. So the mass balance tell us that this node should consume 5 liters per second. But if I'm wrong, so I have a mass imbalance here that, of course, when I use a hydraulic model, a computational basic model, I don't have. So if in one hand we have the strongness and the robustness of hydraulic models, hydraulic computational models, on the other hand, what I have for using meta model are the possibility to encapsulate all those uncertainties on the hydraulic estimation. But maybe I should have a way to congregate both worlds, the hydraulic based models with the accuracy and with the way to use this information that is coming from field without need of calibration that are based on the surrogated model, the meta model. So the question is, can I do this kind of things? Can I merge those worlds? And the answer is yes. In the next slide, we can see how can we do this. Basically, imagine that I have here in the map down the water network, the topology of the network with some blue points that are the measurement points. So I'm acquiring data at real time. I feed a neural network to do the first estimation. So the first estimation basically are based on the error, the classical error of machine learning. So I have the estimated value, I have the real mentioned point, and I do the difference, and I find an error. This error is, let's call this a statistical error or data error because it's completely based on the data of the field. But I could put inside of my machine learning, I could put inside of my artificial intelligence the hydraulic laws that I know. So I know how the hydraulics of a network uh, I know how it works water distribution system. So I could put this mass equation and energy equation to find a compromise solution between high accuracy when I look only to the data to robustness of hydraulics when I take a look to the mass conservation and energy conservation. So basically, we are talking what we call physical informed neural networks. So physical informed neural networks are still artificial neural networks, but using the physical background to build a model that will be more robust from hydraulic point of view and even more reliable when we talk to hydraulic engineers, that we are able to find a compromise solution between fastness, computational efficiency, accuracy, and the hydraulic conditions that I find based on the hydraulic equations of the system. So I want to present you two applications of those kind of models. So next slide, we can see first in the left down point of the presentation, we can see a theoretical case study where we can see the estimation of the system, the error of the hydraulic estimation, and distribution of the error for pressure and flow rate. But here is only an illustration how is the capability of those models, because what I really would like to show you are those two figures. The first one up in the center, up the node one that I'm calling here. This is a real case study that you can see the points on the high colored figure on the right side. So this graph is one point of this right side figure. And what we can see is the behavior of the system. So the red one is the monitored pressure in the system, and the blue one is the estimated pressure using artificial intelligence, using our physical informed neural network. And we have also the confidence interval estimated using this model. Basically, what this figure is showing us is the accuracy of the estimation of the hydraulic system, the hydraulic pressure in this case, but we also could have flow rate. And this is an anomaly. Like we have a drop of pressure that could be super hard for a normal artificial neural network to see this drop, because this is a not common drop. But when we include the physical informed part, we have more capability of estimation of this drop, because this is a normal it's not a normal behavior of the system. But when I see other pressure sensors, other flow rate sensors having some drops, my model is going that direction, because the hydraulic consistency of the system more or less obligated the model to go down and simulate exactly this drop. So this first application is exactly a surrogated model. So basically, I'm entering with pressure in some monitoring points, and I'm estimating the hydraulic state of all the other points, surrogating EPA net model or any kind of computational hydraulic model. If we go to the next slide, what we can see is an application of this kind of models. Now it's a literature case study, but it's an interesting one, because this is a really, really common problem that we face in water distribution systems that are anomalies. Basically, when I see the measurements of the system, those are pressure sensors. So I can see quite a common behavior in the system. So during the night, the pressure go up. During the day, the pressure go down, because people are pushing and consuming more water. So we have the hydraulic head loss in the pipes. And when anomaly arrives, okay, I can see some change in pattern by eyes. Maybe I don't need a really important tool to see this difference here. But I bring this case study to go further with this, because the point is not only finding or detecting an anomaly. The point is where this anomaly is happening. Because imagine that I have here in this network 32 pressure sensors. I'm showing you just 5 pressure sensors. You will understand why later. But okay, I have this pressure sensors. I see a bit of a drop of pressure, but that is an anomaly. Okay, that is an anomaly, but where? And if this anomaly is not so strong, if it's a really smooth leakage, like 0.1 liter per second, that is meaning a shower, only to have an idea about this. So if I have a small leakage in the system, probably this drop of pressure will be really soft, and I could not detect by eye. So the point is what we can do to detect this anomaly, to detect this leakage, and localize that leakage. Because then, if I have a leakage, I should ask people of my water utility to go there and fix this leak. And to find it, imagine that the pipes are underground. So to find it, they should go in a good point. Otherwise, they should open all the streets, breaking everything to find the leakage. So the idea is reducing this space of surge. So in the next slide, we can see what we did using artificial intelligence. So basically, we combined those pressure sensors. For this, I'm showing you just 5 because those pressure sensors are the 5 most important for this event. So using a kind of artificial intelligence, a kind of machine learning algorithm, what we did is combining and crossing those information to see exactly the high probability of where the leakage could appear. So the red is the point, or the darker is the point, the high probability we have to have a leakage there. And what we can see here is our algorithm is detecting the anomaly in this really dark red points, and in truth, they happen really close to this street that we identified as the high probability of finding. So of course we can not tell the company go and open that street. Usually what we tell is go in that region, the red and maybe the orange region, and please do a field check. Probably the leakages are there. So we are basically reducing the search space of anomalies, still using artificial intelligence. So if we go to the next slide, what we can see is an evolution. Some 20, 30 years ago, we started with digitalization. Then maybe 20 years ago, machine learning arrives. Nowadays, we are talking about digital twins, combining digital twins with physics informant, this point that I brought to you today. And the future, we can talk about generative AI. So basically the chatbots and other kind of things that can help the companies for manage the system. And finally, the agent AI. So how able are agents to operate systems, or how robust will be this kind of agents on making or supporting decisions. We can think on automated work for, I don't know, for example, order generation, or this kind of thing that I showed you. For example, we could have an agent responsible to tell the operators, pay attention on that region because that region probably has a leak there. So nowadays, of course, should be someone doing this, but we could train agents for specific tasks that can help and support people. So the next slide, and that is the last one probably. We are doing a really fast overview about this world of artificial intelligence. Physical informant are really important because they bring hydraulics to the data science. So basically, we are not talking different language more. It was a really criticized point in the past, like people using machine learning are not talking about hydraulics, but nowadays we are bringing hydraulics to machine learning and building this kind of digital twins. I didn't talk about it, but one important point are the explainable AI. So basically, how those algorithms that we have, how those artificial intelligence make the decisions, and how we nowadays we can discover the path of information inside of those maths, and then we can understand how this happened. And finally, this support the generative AI that will be the base for the agents. This is what I would like to talk you today. The next slide is the finishing one. This is this last one. So basically, the provocation that I would like to bring is exactly this. How can we use AI on water distribution system to improve the operation and management of the systems? That's it. Thank you. Yeah, thank you.
Oh, thank you, Bruno, for the presentation. It was very interesting, and I think that you just spot the key aspects of what is more important these days for the use of AI for water systems. And then I like it more. The most I like it from your presentation is just how do you emphasize it in the water systems, and also in the hydraulics and expert knowledge that we can get out of the information coming from and the data coming from the water utilities and the water networks. Because I do think the same that at the end you just wrap up with the physics informed machine learning. I do think that this expert knowledge is highly valuable these days, and we cannot forget from the most AI we use, we are also solving an engineering problem and engineering questions, and the AI is going to enable us. It's going to enhance our decision making capacity, but it cannot just rely in AI only. And just in that part, the options and the ticks you just mentioned about explainable AI, physician form AI, whatsoever, I do think are the most important areas that we can work today on improving and enhancing AI in for water systems and urban water management. Anyway, yeah. Thank you very much. And then I don't know if there are some questions, Jyoti, if you have. Uh,
Yes, there are the Q&A. So should I start reading the questions?
yeah, that could be fantastic. Because I just try to answer a few of them, just writing, but I think there are more
Okay,
than a few. So
okay.
just do it.
So from Rebecca, many wastewater and water treatment plants in developing countries experience intermittent operation, limited instrumentation, and incomplete historical data. What practical AI applications can utilities implement today under these constraints? And what would you recommend as a first step toward building an AI-enabled utility? Whosoever can answer.
Yeah, Bruno, go ahead.
Okay, so thank you, Rebecca, for the question. Yeah, it's true that in mainly in developed countries we have this challenge. Um, I guess first of all, it's important to invest on monitoring systems. We cannot talk about artificial intelligence without data. So basically, the first step is exactly this digital transition for taking information of the system that we have, and then, of course, if we have data, many things can be done. You can build predictive models of those data, for example, pressure, demand, flow rate, quality, depends of what we have. Um, from my experience, I'm from Brazil, so we are facing some experience exactly in this direction that new water utilities arrives in a city without any kind of information. So the first investment that they do basically are monitoring, so flow rate and pressure. And then with this, they are quite able to, for example, discover leakages, discover how is the real built system, because even sometimes in some cities in Brazil, for example, they even don't know where the pipes are. So yeah, I would say in this direction of investing on monitoring and then doing something with this data.
And also, I think that as you mentioned before, they embrace the uncertainty. So there are many things we are not going to know. There are deep uncertainties in that case, and I think that could be a good direction as well for the models to use. Is that models that embrace this uncertainty? Let's say, or let's mention this Bayesian modeling or Bayesian machine learning style of work. That could be a very interesting avenue of research and models for this problem.
Okay, so then the next question is for Bruno. What are the principal parameters in water supply system that permits to install or use AI to control pressure and water quality?
Mm. I don't know if I understood really well the question, but the most important parameters that we could use for better control of system would be forecasting the demand for sure. Demand is really important, thinking operation. And thinking on quality, depends a bit about which kind of system, because some systems, for example, in America, the American continent, almost all of them countries use chlorine, for example, for treatment of water. So a predictive model of chlorine could be super important to be tracing for controlling and understanding the water quality. In a while, if you go, for example, in other countries, you don't have chlorine, you have another kind of treatment. So the parameters change a bit, I guess, for quality. In a while, for operation, I would say for sure predicting water demand is really important, and then predicting pressure on the specific points, like high points or really sensible points, usually high points, are important for keeping the operation going on. Yeah, I guess this, if I understand well, the question is this. Yeah.
You can add manual if you wish. Like,
No, I was totally agree with Bruno. I mean, again, uncertainty. I mean, I love probability, and then I love uncertainty and deal with that, and then the same happen as well, because we have all these parameters. We can read these parameters, but we need to acknowledge that the sensor deployment we're going to have over the network is going to be limited anyway. So they're going to be part of a large part of the infrastructure that is going to be unobserved. So we need to infer what the states with respect to the pressure-driven states, but also the water quality parameters, they need to be inferred as well. How is going to be the evolution of these parameters along the network, and that in that part is going beyond the parameters that needed, that Bruno covers very well, but also the models we need to use to deal with them. They need to acknowledge this part of uncertainty, in the sense of we're going to be very certain when we are having a sensor out there measuring it directly, but we are going to just spread uncertainty and know what is going to happen just far away from where the sensors are placed.
Thanks. So I will go to the next question by Saeed Azadi. What practical AI approaches can utilities implement to identify, monitor, and predict temporal changes in micropollutant clusters and emerging contaminant profiles within water and wastewater treatment systems, especially under conditions of limited sensor coverage and incomplete historical data?
Bueno, okay. This is a large question. Thinking on algorithms nowadays, I guess the most important ones are based on graph convolutional networks and things like this. Linking the topology of the system based on graphs and the physical informant part. So I guess this is maybe the top approach that we have nowadays for water distribution systems. This can be useful for hydraulics or quality. Is the same. The main structure is the same. So I would say on this direction of graph combined with physical informant things are really important. Of course, when we think on incomplete data, again, Manuel commented, we have the uncertainties. The higher is the more incomplete are the data, the higher are the uncertainties. So I guess we can bring to those kind of models the confidence interval, as I showed on the gray figure, because then we know how trustable are those estimations. Yeah, I guess if think on algorithms are this kind of things. Man, I don't know if you want to complete something.
Just to complement a little bit, it's just I will, with respect to the modeling part of it, I will just think about also time series. Maybe we just are having a track of the water quality of the problem, and then we may have some kind of change point detection or matrix profile for anomaly detection at the end of the day. As you mentioned in the presentation, Bruno, I think is that could be key for that. But also, if we're having no continuous data or sparse data, we need to return to this to deal with interrupted time series analysis and other type of analysis from the more time series point of view. But also, of course, we can just think about we having a sensor network that is going to be measuring exact points of the infrastructure we are going to have, or the water network, and then the graph analysis and the graph convolutional neural network, as you mentioned, should be one of the key elements of it. Again, just aiming to do some anomaly detection and to spot when parameters change abruptly, or when we have some kind of anomaly, or let's call it discord. This is the right word, because anomaly is anomaly when it's confirmed that it's something wrong, and otherwise it would be just a discord. But it's only my view. Thank you.
Thanks, Manuel and Bruno. So the next question that we have is by Prajwal Shrestha. Can AI and ML be used to do structural and non-structural adaptation of water treatment system in the change of effect of climate change?
Well, climate change is a good question all the time, because this bring a new source of uncertainties. I am pretty sure that artificial intelligence, or all the machine learning algorithms that we are talking today, are really able to handle this, thinking that we are not talking about a defined last answer, a complete precise estimation. Mainly think on climate change, but we are talking about trends. So if you are able to estimate the trends of the systems, like what I'm talking about trends is river level will be lower, so thinking on water treatment, or the underground the underground water level will be decrease a bit or increase a bit. So if we are able to estimate trends based on long-term climate models, then we can have an idea about what is happening for the future, and this can support us to do structural or non-structural changes on treatment, or even for the distribution system. So what I think is, again, artificial intelligence or machine learning are not doing magics. Basically, are handle data. So the higher is the uncertainty, more careful should I be using this information. Yeah, I have this perspective thinking on data and machine learning and climate change.
Thank you.
Yeah, I got an extra reflection about it.
Yes,
in the sense of, in general, by default, them all of them, or not most of them, by default, the machine learning models are based on average, and then are just regression against the average, and doing the estimations with respect to the mean values. We may need to think also what happened in the extreme data. And I think that all machine learning algorithms just tailored for extreme data could be an add-on to consider in that case. But anyway, Bruno, that also remind me of this battle of for the water networks that we just compete in the conference the 2 months ago, about how it's going to be affected an area, a regional area, the water resources, the population growth, and all the environmental pressure, and also how is going to be the response on the water management for that, right, Bruno?
Yeah, even the economy, Manu, if we think, because this change, for example, price of energy that affect directly the operation. Yeah, so we talk a lot of climate change, but even the economy change can affect a lot of the operation of the systems. Yeah.
Okay, thank you so much. So we go to the next question by Jose. And this seems to be interesting. Like, what happens if the AI makes a wrong decision or the system goes down?
Wow.
We're in trouble.
Exactly. I guess it's the same idea of autonomous car, If an autonomous car make a bad decision and has an accident, who is the responsible for this? Is all the time an ethical question that I guess is still on discussion. I don't have an answer for this question. I guess I have a reflection for this question. I don't know, man, if you want
The
to
human
start.
in the loop is the main question. So the automation is a paradigm that is a beauty forget about the human in the loop to control the final decision, and not just to blame the human in the loop, but to be sure that things make sense. And also, all these explainable you suggested with the self-driven cars is part of the okay. What is if we are doing the model wrong? What was being wrong? How can accountant in the model, where was the error in the model? Was the data input, was some part of the model that didn't went well? What didn't work? And that is the good question that needs to be flagged by the own algorithm, other algorithms controlling this algorithm, but also the humans, they need to flag it as well. So we can just add several layers of it, and then just to help out when the model is grown to realize that they are doing grown and decisions. But still, all the decision for approach, for instance, can help out to say, okay, could be grown or not, but at least it's physically consistent what we are just estimating here. And other parts about explainability and human in the loop can also help in this regard.
Okay, so I think we should move to the questions quickly by Henry. So how can water operators in Latin America adoption state implement this digital twin framework progressively to optimize supply networks despite systemic underinvestment in operations and maintenance?
Okay, so when we think on operation maintenance, the cost involved on this is super high. Then, of course, machine learning can help us trying to reduce this cost. We have some experience about, for example, optimal operation of pumps that can reduce really a lot the energy consumption and other kind of things. Not only energy consumption, but also, for example, when we think on optimal operation, we can also reduce, for example, the treatment products consumption, etc. And of course, when you go to the management or more open window on the direction of leaks, for example, I guess machine learning is helping a lot. I see and I saw and I still want to see more applications of machine learning in real case in real companies for detecting and localizing leaks, for example. That is really important problem of water system. So I guess the support is exactly as we commented in the question before. Those tools are like for me, it has the same role of computational models, EPNet, for example. They support the decision. So if they have a good support of the decision, improve a bit what we can decide later, it will be better. But I don't think that we can leave exactly alone those tools for making decision, thinking on a super magic power of those systems, but more as a support decision tool. Manu, I don't know if you want to complement something.
No, nothing to add. You just been super accurate. Thank you.
Okay, so I move on to the next question quickly because we have a couple of other questions as well. So how do you address agenting governance when using AI agents, deterministic or non-deterministic?
Manu, would like to start you with agents?
Yeah, I mean, with respect to the AI agents, in principle, where just the examples we work with them are deterministic approach for the AI agents, because we need to deal with a lot of uncertainty in the system when we have a system of agents that are just bringing some kind of uncertainty themselves in the answers. Still, the agentic AI for monitoring and controlling and having intention on self-learning of the system, they need to be also some kind of controlled by a layer of rules. The good old symbolic AI. I do believe they need to have a game to play here with the agentic AI, just to guarantee again that we are not only just learning from the scratch and from the database we have, but also we are reasoning somehow in the sense of we can just think and have a minimum level of reasoning that are going to guarantee we are going in the right direction. Again, to avoid kind of hallucinations and just be real focused on that. So in principle, as the uncertainty is coming by the you cannot control at all what is going to be the outcome of all this agent system. But at the end of the day, each of the agents, they are going to have some kind of rules that are going to just be go through them and learn from them, and then they are going to just be in that sense deterministic in principle. That can be complicated in the future, but we need to add this layer of self-learning with reasoning behind them. Otherwise, we just don't know, and we can trust even less on what we have from that system. Bruno, I think you have something to say.
No, I was thinking it's like a self-learning process, you know. When I don't know, imagine that we have an agent for optimal operation of system. Then you have an operator that validate this suggestion of operation. So basically, we are learning to the agent again that based on those contexts. The operation was right. So basically, we are reinforcing learning the process of the agent. And again, the filter is the human. We cannot forget it, I guess. All the time, the last decision should be done by humans, at least for now. I don't know for the future, but at least for now, I still believe that humans are super, super important on the process. Not only for the process of the decision, but also for the process of the reinforcement learning. Yeah.
Okay, so I will move to the next question by Sergio. For an AI-based multi-twin approach in urban water systems, how detailed and reliable does the network asset registration need to be? Also, compared with the more traditional approach, how much additional pressure and flow instrumentation is typically required to achieve reliable results?
For my experience, not that much. What we are doing nowadays are based on what the water utility has on field. So I am working with some real companies in Brazil. Sorry to say real companies, but it's quite common in our field working with literature case studies. So when I talk real companies, I'm talking about water utilities that has a water system. So we are working with some of them in Brazil, and we are working with the pressure sensors and the flow rate that they have. It's quite hard to say how much sensors we should put there or compare with a more classical approach like a computational model. How precise it will be depends a lot of the dynamic of the system. But for my experience, for example, bringing the physical informant part for the learning process, we could do good result. We can have good accuracy even if with few data or few points of measurements. But of course, again, this depends a lot. When we go for I don't know, for example, Rio de Janeiro, that is one of the largest city in Brazil, we are talking about 2,000 sensors. You know, when we go for I don't know a small city, in Brazil we are talking about 30 sensors. So this depends a lot of the scale of information that we also want to have.
Okay, thank you. Bruno, so the next question is by Mohammed Ali. How successful is your model in detecting leakage within water distribution networks, considering that leakage events can range from large, easily identifiable bursts to very small background leaks that induce pressure changes smaller than the accuracy limits of the pressure sensors?
Success is an important question. How successful? I don't know. We are talking about detection of 0.5, 0.2 liters per second. That is quite small, like 2 showers. Refining around 50 to 100 meters of distance of the localization with real data based on data from Brazil. How successful? We compare with what the company had before. I guess this is a quite interesting rate of successful because if we can improve what they had before, I guess it's already something, and we did. Basically, we are improving more than not exactly the detection. The detection was from company was quite good because they used the night flow information for detecting leaks, but the reduction of the search space is really considerable for that company. So I guess we are going more in the direction of reducing a bit the efforts on finding the leakage than detecting the leakage. Yeah.
Yeah, and
So the next, yes,
we
yes,
are about
please.
just to we are about just to think that on new technologies as well to be used on these. So it's not only AI but also the new disruptive technologies that use some satellite images just to detect its background leakage, so humidity on the ground, right? So we can also use CCTV images, and we can just mix all more information. So it's not how successful has been so far, but also the future we have in front of us for even improve those that numbers on leak detection that we have at the moment, because we have everything and more data available, more source of data, and we have the tools of machine learning tools and open AI just to work on into it and get even better results.
Just a complementation, man. I guess go exactly on the direction of information fusion that we comment
Yeah.
sometimes ago. Uh, More and more source of information can reduce a bit the uncertainty of other source of information. So we are congregating things on this direction of information fusion. That is super high topic, I guess. Yeah.
Yeah, I think so.
Okay, so I would like to take now the one or two questions more because after that we have to wrap up and end the session. So by Arturo Noga, so for Philippines. So just want to ask you if you already have a technology to gather real-time data of the pumping water level. We are using a groundwater source defill.
Well, we can have sensors for getting this information, right? We are not developing sensors in our case. Also, I know in the case of Manu, it's not the case of developing sensors, but we use those information. But from pump stations, you can have many source of data. You can have, of course, pressure flow rate. That is the most common, but also you can have vibration. You can have accuracy data. You can measure energy consumption. So all those things can help you to do a digital twin, for example, of a pump station or a underground pumping system or something like this. It's not what we are doing today, but it's we handle with that data for sure. Yeah, with the normal
And to
actuation.
complement that, we are not mentioning here because we talk about a lot about sensors and and all the AI, but we think that this is the digital twin platform we can build from the pump station, right? So with this well sensor, then it's going to transmit real time or near real time data to the digital twin, and the digital twin supposedly is going to just have a detection of information as well to the real infrastructure. So we are just talking of these pieces and elements of digital twin all the time, but we don't mention much digital twin, but it's most of the time is what we are just referring to and
Mm.
talking to actually.
So the last question I would like to take up is by Malak Maita. I'm managing a project that using AI and digital twin for network management and recommend best operational scenarios in Jordan. When and how frequently should I do a model training?
Hmm.
This remind me to Brentan et al. 2017. This is your paper, Bruno.
Yeah, exactly. Uh, I guess again thinking
Many
on
years.
optimal operation.
Ago.
Thank you, man. Thinking on optimal operation of systems. We all the time are talking about the uncertainty of demand. So we should know the demand, at least an idea to decide um, what will be our operation. So if I would say a recommendation, I would recommend estimate the demand and try to use a classical. This is the best, not the best, sorry. This is the basic one. Estimate the demand and use a classical hydraulic model. But you can also surrogate the hydraulic model for another artificial intelligence. So then we are coupling and linking artificial intelligence for doing some part of the tasks, and then an optimization for the optimal operation. That's it.
and
Brenton
control the
training.
error. The moment the error is going so high, then it's time to train again.
Yeah, exactly.
So thank you so much, Bruno, Manuel, Aaron, and Branda, for contributing to this wonderful webinar and presentations. So the participants can mail their questions, the ones which have not been answered, they can mail their questions to Bruno, Manuel, and me also. So we will answer them. Is it fine, Bruno? Or
Yeah,
anything
sure.
additional which you would like to add here?
Sure.
Okay. So, Erin, anything from your side if you'd like to add?
No, just it was a super nice discussion about what we love to do.
So, thank you so much. Thank you so much, everyone.